Hello everyone, welcome back to the course Vector Calculus and Complex Analysis. Myself Dr. N.CH.Ramgopal, working as Associate Professor in Mathematics in the Department of Humanities and Sciences, MLR Institute of Technology, Hyderabad. Today I am going to discuss about a method of evaluating the integral of the form minus infinity to plus infinity e power I mx f of x dx. So, the evaluation of integral of this type, the limits are from minus infinity to plus infinity and the integrand is e power I mx f of x dx. So, to evaluate this, first you should know the Jordan's lemma or Jordan's theorem. So, if f of z is analytic except at finite number of singularities, if f of z is analytic except at finite number of singularities and f of z tends to 0 as z tends to infinity, then limit r tends to 0, the line integral CR e power mx f of z dz is 0. So, again here this CR is the semicircle mod z equal to r, the semicircle mod z equal to r. So, the line integral along this semicircle becomes 0. So, that vanishes. That is Jordan's lemma. It helps us in evaluating the integrals of the form integral minus infinity to plus infinity p of x by q of x sin mx dx or cos mx dx, where m is greater than 0. So, here p and q are polynomials and the degree of q is greater than the degree that of p, and q of x is 0 has no real roots. So, we can use this Jordan's lemma to evaluate the line integrals of this particular form. Either we may have sine function or cosine function. So, let us discuss this through an example. Here, evaluate the line integral from minus infinity to plus infinity cos ax by x square plus 1 dx, where a is greater than 0. We need to evaluate the integral from minus infinity to plus infinity 1 by x square plus 1 cos ax dx. So, which is in the standard form of some p of x by q of x into cos mx dx. So, where m is greater than 0. That is why here given a is greater than 0. Now, how to evaluate this? In fact, we are discussing about a method of evaluating the definite integral of the form minus infinity to plus infinity e power I mx into f of x dx. So, here this cos ax is the real part of e power iax, because what is e power I theta? Cos theta plus I sin theta. So, e power iax is cos ax plus I sin ax. So, this cos ax is the real part and sin ax is the imaginary part. So, I consider the line integral C f of z dz as in the form line integral C e power iaz f of z dz. So, here in the expansion of e power iaz, cos az is the real part of this e power iaz. So, therefore, we by taking the integral of this form, we can evaluate the given required one. Now, line integral C e power iaz 1 by z square plus 1 dz. So, e power iaz by z square plus 1 dz. So, here how to find the poles? By equating the denominator to 0. Z square plus 1 is 0, z square is minus 1, z is plus or minus I. And here let C be the curve consisting of semicircle CR, which is mod z equal to R. So here this is the semicircle, and hence Z equal to I only lies inside this upper half of semicircle. Z equal to minus I lies outside that. So hence we need to find the residue of F at this pole Z equal to I. And here Z equal to I is a simple pole. Z equal to I is a pole of order 1. So is a simple pole. And how to find the residue of a simple pole? Z tends to A. Simply limit Z tends to A, Z minus A into F of Z. So residue of F at Z equal to I is limit Z tends to I, Z minus I into what is the function F of Z. So here the function is in the form of e power IAZ by Z square plus 1. So e power IAZ by Z square plus 1, and this Z square plus 1 can be written as e power IAZ by Z minus I into Z plus I. So Z square minus I square, where I square is minus 1, so Z square plus 1. So these two gets cancelled. Now Z tends to I, e power AI square by 2I, but I square is minus 1. So e power minus A by 2I. This is the residue of the function F of Z. Now we apply the residue theorem to evaluate the line integral C of the function F of Z dz, which is 2 pi I into sum of the residues. So the given is in the form of minus infinity to plus infinity 1 by x square plus 1 cos ax, x square plus 1 cos ax dx is 2 pi I into sum of the residues. Here we have e power minus a by 2a, e power minus a by 2I. So here 2I and 2I gets cancelled. So pi by e power a is the line integral of the given function. So in today's session we have discussed about a method of evaluating an integral of the form minus infinity to plus infinity e power I mx into f of x dx. Here we introduce a curve having a semicircle, and as r tends to 0 infinity, that line integral along CR also tends to 0. So you, and also by finding the poles and residues and then using the residue theorem, we can evaluate the given line integral. So in the last during the last 3 sessions we have discussed the method of evaluating real definite integrals of the form. The first one is integral from 0 to 2 pi, a function having sin theta and cos theta, and second minus infinity to plus infinity f of x dx, and third minus to plus e power I mx f of x dx. So the contour integration helps us in evaluating these real definite integrals. So in the next session we are going to discuss about conformal mapping, so which is the last unit of this course. So this is for today's session, and we will meet in the next session. Thank you.